Right. So welcome everybody. Today we are offering you a webinar on Ansys HFSS solution. We will start with an overview with a bit of use cases, and I'll hand over to Shawn Carpenter
Very
now.
good.
So Shawn, you can start and just thanks for sharing your slides so we can see it, and you can go ahead. Thanks a lot.
Good, Laura. And if I could confirm, you're hearing me okay?
I can hear you, yes.
Excellent. Well, welcome everybody. Thank you for joining us today in your afternoon. My name is Shawn Carpenter. I serve Ansys as a program director for 5G, 6G, and space applications. And it'd be my pleasure today to talk to you about our high fidelity physics simulation for high frequency electronics, apertures and antenna systems, radar signatures, and some RF propagation. So a lot of things to cover under that umbrella. So we'll go ahead and jump right into it. There's a lot to talk about here. We don't need to wade through this entire slide, but I did want to give you a sense for the areas in which Ansys is a solid application and to provide some of the tools or show you some of the tools that we offer. This is the Ansys stack. We are a simulation company. We are 100% dedicated to simulation. We don't do hardware modeling or hardware building. We don't have test laboratories. We are about building the tools that designers such as yourselves need in order to virtually prototype and design your products and validate the designs and of course also optimize them in a virtual environment or in a virtual format. So there are something like 90 plus Ansys products. Our bedrock is the physics-based simulation tools that you see across the bottom here. Very full stack, very complete tools, best in class for the physics of structural analysis, fluidic analysis, electronics analysis, which will really be the subject of what we'll talk about here today, semiconductors, optics, and photonics, a very complete set of tools for optics and photonics, and then 3D design under our Discovery products. But one thing that's important when you're doing multiple physics and multi-physics simulation, because we also couple these physics together to create an understanding of what happens in your product as you power it and it heats up and then it deforms and things like that. It's important to drive this with good material property information, and we have a unified material property database that supports all of the physics across the board to provide the appropriate physics, material properties, and characterizations that you need to input to each of the physics or to multi-physics simulation that you may use. Now that's important because it provides a single authoritative source of truth for material property information. This is both the basic materials, the things that would maybe come out of your chemistry handbooks, but also contains the world's largest vendor supplied database of man-made and synthetic materials, including RF boards and products. So just check that out. Be aware of that in case you do need to have material properties indexed back to like a vendor characteristics and so forth. Now, another thing that we're really big on here lately is validating your products as they operate in the context of a design reference mission. If you're building an antenna, that antenna may be designed to mount onto an aircraft. That aircraft is intended to fly through an environment, and you might want to model it through its engagement as the aircraft goes through its typical maneuvers. And for that reason, very recently, we added to the Ansys family a digital mission engineering package when we acquired a company called Analytical Graphics Incorporated, AGI, about 4 years ago. And you'll see some examples of that as I walk through here as well. I'm not going to concentrate on the mission engineering, but I will briefly introduce you to it. And then, of course, all of the tools that you would expect for cloud and HPC deployment, for large scale computing when it's needed, optimization tool sets and tool sets to handle training AI and things like that, process and data management for very large multi-space characteristics that you get from many simulations, and then the multi-simulation of multi-physics. So let's one last point that I want to make here too is that while this may seem and feel like it's a closed environment, we are in fact a very open ecosystem. Ansys does not have a product lifecycle management package, a PLM tool within our product suites. Therefore, we are PLM agnostic and CAD agnostic. So we will work with pretty much any computer-aided design package that you might have out there, and integrate. We will integrate within our model-based systems engineering constructs tools that come from other vendors. This is not a closed environment. This is an open environment. You may be already using a number of other tools from a variety of vendors, and we need to be able to accommodate that if you're going to do model-based systems engineering and mission engineering. Okay, enough of that. Let me just give you the roadmap for what I'm going to be talking about today. We'll start with design and reliability of high performance electronics and RF systems. I'll work my way into antenna systems and emissions. We'll talk a little bit about radar signature disciplines, and then into the process of um, dealing with and mitigating onboard interference, co-site interference effects when we have multiple radios or multiple emitters on the same platform or in the same local area. We'll briefly touch on a capability for modeling electromagnetic pulse, and then I'll finish up with a new product and a new set of offerings from Ansys here for real-time terrestrial wireless channel modeling and near field radar and radar imaging applications. But the point is to be able to do this stuff at real time. So we'll hit that right at the very end. So let's start with design and reliability of high performance electronics and RF systems. Now, to accomplish all of this simulation, of course, it takes a family of products that can handle things from the very small to the very large if we're going to be able to provide an integrated modeling and simulation capability that is based on rudimentary physics, on Maxwell's equations, and on the basic set of physics principles that govern these structures. So we start with a capability to model electronics. That is things from the transistor gate size feature to perhaps an entire integrated circuit to capture signal integrity, power integrity, and EMI emissions and so forth, to the packages in which those ICs sit. So you may have interposers, you may have package interconnects, you may have wire bonds, you have a very complex package, potting structure. That package sits on a board. You want to model the interconnects to the board. The board may have emissions, may have crosstalk. We need to be able to capture and model these things in a way that we can relate then to our functional systems designs. And we do this with brute force electromagnetic simulation at speeds that you would be quite surprised at. Now, going beyond the board and the circuit level, we also have a large area of applicability in modeling antennas. And as you see, we do a great job of modeling and capturing finite phased array antenna designs, in addition to individual antennas, which can be synthesized, optimized, and work through the parameter space of a particular design within our electronics desktop package. And if you can model the antenna, then you can model the antenna placement on a vehicle. I'll talk about the techniques that we use to do this, but we hybridize through multiple EM analysis techniques in order to then accomplish, for example, the performance of assessment of an antenna as installed on a platform. And if you can model one antenna, you can model multiple antennas to capture wideband coupling effects under the influence of the host platform into which the antennas are integrated, and attach radio models with broadband emissions characteristics and broadband receiver characteristics to capture the RF co-site picture and to begin to work with your system to mitigate some of the interference effects. We also can model transient electromagnetic effects such as lightning strike. That tends to be a lower frequency kind of application space, but fits very readily into the things that we can do, as you can see there. A large area of applicability is radar signature work for both components and also entire vehicles. If you want to model, for example, the radar cross section of an aircraft carrier at 94 gigahertz, that's something that we can do with some of our techniques. We also want to be able to capture large scale platform integrations so that we can look at, for example, field strengths around personnel or around ordnance or other features in the problem, or just model the effect of interaction of multiple bodies in motion or in static situations to capture the RF picture for the connectivity, to capture multipath and so forth. And then on the larger end of the scale, when one needs to capture and model electromagnetic pulse, we can model like entire island-sized structures or city structures, to then capture the coupling of pulse into some of the structure throughout the city or throughout the environment that we're modeling. So this is kind of an overview of the things small to large. Here's another way of looking at it that is set into the context of 5G telecommunications, 5G, 6G telecommunications. And I think one of the takeaways here that I'd like you to get as you look through that top set of features, we are modeling things from nanometers to kilometers here, and that actually can be solved in the context of a single analysis flow that's hybridizing multiple techniques together. So we are able to model things as small as a nanometer. Quite often, customers are using our tools for modeling IC features and RFIC and MMIC features, but then to also model a growing level or a hierarchical level of integration to get to progressively larger structures so that we can then look at emissions, power integrity, signal integrity, electrostatic discharge, all the usual things that we need to be able to characterize when we're working with a virtualized model. Same thing for antennas, starting with something at the elemental, the element level and building to larger constructions until we place these things into the context of a city so that we're modeling things on the order of kilometers. And I'll show you some new technology for accomplishing this. Now, this is not just, excuse me, as I mentioned before, this is not just monophysics, it's not just electromagnetics, but in fact, we are coupling the ability to do power analysis with coupled thermal simulations to get signal integrity and RF and electromagnetic emissions to then capture the impact on structural integrity. Some things get hot, they might deform. If they deform, especially for tuned structures, they may detune, and we want to bring that back to the electromagnetic solver and assess the the quality of the tune and see what we need to do to compensate, or maybe we want to look into using a different material choice, or whatever the trades are that you typically work. We also have a complete reliability stack to give you the mean time to failure for a structure like an entire circuit board or for some kind of component that you're building, simulating the construction and multi-physics of systems together so that you get heat and radiation and so forth, and then set that in an operational sense into the context of an entire city. For example, like for that 5G base station structure. Now, we also, for those working in electronics, have incorporated an entire multi-physics reliability workflow within our electronics desktop, where the designers are working with things like packages and boards, and they wish first to do their signal power integrity, electrostatic discharge, and EM emissions modeling here with coupled models to the packages. You can also take that result and bring it to our thermal simulation, where then you can look at heating profiles under conditions for passive and active cooling, and then take that and bring it to a structural reliability simulation in the mechanical sense, so that you could see what kind of stress you might put on wire bonds and include the impacts actually of vibe and shock analysis and things. But all of this can be done within the Ansys electronics desktop, where a typical electronics designer works. So there's a lot of these mechanical engineering issues that are pretty straightforward for an electrical designer to handle, for at least for early assessments. And then if the need is there to kind of throw it over the fence to a mechanical engineer for really detailed design work, of course, these designs can flow naturally then to our mechanical physics or to our fluid flow physics tools. Now, we also have, as I mentioned, a complete workflow for RF system reliability lifetime analysis to predict, for example, the mean time to failure or the 90% lifetime or whatever lifetime window you need for a complete populated board. And that's under our Sherlock products. I'm not going to talk any more about that, but just know that that is a complete multi-physics coupled analysis flow with component level information, so that we take into account the reliability of every component that's populated on your board as you then apply a physics simulation to the board itself under duress of power up and all the things that we do, heating and so forth. So I mentioned earlier that it takes a number of solvers. It's not too, the set is not too large, but it does take a family of solvers to accomplish all of this. And so when we're working with things at with very high detail, like antenna designs, board designs, chip designs, These usually are things that have very complex arrangements of geometries and can have very exotic materials. There may be ferromagnetic materials, materials with tensor permittivities or tensor permeabilities that are different in each of the three dimensions and depend on the space in which they're located. These are things that we handle with our flagship finite element solver, which is our Ansys HFSS tool, which is probably our most well-known solver in the Ansys family for electromagnetics. HFSS uses finite element simulation. It's been an industry standard now for about 35 years. I used it when I started my career as an antenna designer 34 years ago in an aerospace and defense company. So I know it's been very well validated here over the years. And probably the major advantage that HFSS has is that it meshes exactly to your geometry. There's no approximation. We make your geometry our geometry for the mesh. And the meshing is automatic. You don't have to go in and set features or find certain set points and things like that. It is completely automated in meshing and will converge the mesh depending on what it sees for gradients and so forth in the problem as processing continues. Now that's appropriate for problems up to about 20 electrical wavelengths in size, maybe 100, depending on the complexity of your problem. But you do get to a point where the processing can take some time because it's a full 3D volume meshing approach. So in order to accomplish larger problems or to take some of the smaller problems which are meshed with finite elements and set them into the context of a much larger problem, we have developed fast method of moments, which are surface meshing tools, integral equation methods. That's with our HFSS IE for integral equation method solver is all about. So here you could take a finite element simulation of an antenna and place it at an appropriate position on some mounting structure, a parent structure, and tell the solver that the large geometries you'd like to mesh with a surface meshing approach, and it will automatically hybridize. It'll take the solution of the finite element simulation region and impress it onto the integral equation method region. And this is a great way, and it's all automated, so you don't have to make any great decisions about how you do the meshing and the controls that are set. It will automatically converge in its meshing. But this is good through about 100 to maybe 200 wavelength type problems. So think like a VHF antenna mounted to a mid-sized aircraft. That would be around 100 to 150 wavelengths. But there are certainly problems that are much larger than that. And then we need to turn to yet another hybridization technique here where we use a shooting and bouncing rays approach with the HFSS SBR Plus solver. Now, this uses ray tracing. It is an asymptotic technique. It's based on the physical optics framework. So it's a very accurate kind of a framework that's recognized as a preferred method for doing radar signature modeling for very large targets where very fine detail and resolution of a target is necessary. This, again, is another technique that can be incorporated into the solution flow so that, for example, an antenna that would be mounted on the superstructure of this ship, the antenna could be solved as a finite element simulation region that is captured as a near field source, which then is applied to a shooting and bouncing ray simulation to compute coupling to other antennas distributed throughout the superstructure or across the ship, or distributed in some really large environment. And here we can solve problems that would be anywhere from about 10 wavelengths, maybe 50 wavelength size problems up to quarter of a million or half a million electrical wavelengths. It's a very good solver for large space problems. And as I've said, these are all automatically hybridized when you incorporate the appropriate solver for the appropriate size and complexity of the problem of interest. Now, of course, you can also force multiply many of these simulations through the use of HPC. We can do 2 and 3 level distributed computing and offer capability on a variety of cloud computing providers. I won't spend too much time going through all of that, but one of the ways in which you can, for example, use finite element simulation for even electrically very large problems is to employ our automated divide and conquer methodology that would break up a particular region into several subdomains and process the subdomains on separate computing nodes, and then of course bring everything back together again to create a complete solution for things like radar scattering or installed antenna performance modeling. So just know that we have very significant capabilities for force multiplication through high performance computing capabilities. Now, let me talk about a few applications that are kind of interesting here within this subspace that I mentioned before, RF apertures and installed antenna examples. This is the process of both getting a very accurate model for a particular antenna or antenna system, and then also simulating it in place on a particular host platform. And here you can see an example where we've modeled multiple rotations. We've actually run a parametric sweep analysis so that we can capture a three-dimensional far field pattern along with a couple of principal pattern cuts for I think this is a 5.9 gigahertz blade antenna that's modeled on this V-22 tilt rotor aircraft. And there are, I think, about 150 simulations actually that were done throughout this. And as you can see, the total simulation time when you use these hybridized techniques is about 22 seconds per position on what's actually now a pretty old laptop using an NVIDIA RTX 5000 GPU for the shooting and bouncing ray solver. So here we have a finite element simulation applied to the antenna, and then a near field capture on the region around the antenna that's placed on top of the vehicle, and then shooting and bouncing rays is then used to capture the coupling of that near field source on the rest of the body, capturing all of those blockages, interactions, diffractions, all the things that happen here. Now, if you don't have an antenna design, that's okay. We carry inside of our HFSS package and in the electronics desktop an integrated antenna design and library so that you can synthesize immediately, over 70 topologies, synthesize, initial designs for antennas or capture designs of antennas that are topologically similar to something that you're concerned about. And it will completely build up a full 3D model of the antenna built for the band that you've indicated, in this, worksheet that it presents to you for the type of antenna that you've selected. All of the output reports are set up. The analysis conditions are already provided for you. And you can basically just punch the go button and simulate the antenna that you've synthesized. It's also fully parameterized so that you can then go in and optimize the design or push it through a parameter space to understand how its sensitivities and how you might tune or improve it. All right, and there's a kind of a snapshot here of some of the collection of the 70 plus topologies that we can synthesize immediately, ready for simulation. Now, using this, we've also synthesized a circular polarized wave feed waveguide horn, and that is actually under the radome of that helicopter. It's actually illuminating a reflector antenna that then is solved under that radome, and we're capturing and modeling the change of the rotors. Actually, it's an installed performance model here, but we're moving the rotors, and there's also a tilt, an elevation, and azimuth steering going on with the antenna system inside of the radome. And so you can see here a couple of ways of presenting the far field pattern. That's what you're looking at, is a globe projection there. And you can see as it steers back and looks toward the tail, of course, we get a fair amount of distortion in the beam and the side lobe levels rise. But this is an example here where we've conducted we punch the solve button once and we get a hybrid simulation that does a finite element simulation on the feed horn and then models its near field interactions with the reflector, the radome, and the rest of the platform using the shooting and bouncing ray simulation. Of course, you can set antennas in place. Some of those antennas can be very simple to very complex physics-based designs. This is an example. We just took a 1 gigahertz wire monopole filament antenna, placed it above the superstructure or on the superstructure of this particular frigate kind of ship, and then computed near fields and far fields. So you can get a look at both. You can simulate both at the same time across very large regions when it comes to the near fields. So very straightforward for capturing, again, HERF and HERP and HERO, field levels near personnel or near ordnance and things like that. Now, HFSS is particularly well known for a really great technique for capturing models of phased array antennas that are finite in nature. And when we model finite phased arrays, we're particularly concerned about mutual coupling effects as well as the edge effects and the corner effects, and also coupling effects on the array that come from radomes or other unusual structure close to the antenna. And so we have the capability to break an antenna down, particularly periodic antennas, down into unit cells and design phased arrays. And this design process begins by optimizing a particular unit cell, then setting it into the context of a larger array. And some of these cells may be just things like the corner. They don't actually have antennas in them, but they represent part of the finite structure of the antenna, which will be important on the matching characteristics of each element as well as the radiation characteristics. Right. And so we've developed a technique called 3D component design decomposition or domain decomposition, which will leverage unit cell simulation models and then put them into an iterative solution with a collection of other unit cells to give you very quickly a very accurate model for the array that will be representative, give you, wideband feed point characteristics, S parameter characteristics that are appropriate for active array considerations, active element considerations, and then would enable you to do beam steering studies so that you could drive any excitation against this thing that you want to look at single beam and multi-beam simulations, beam nulling, right? And you can depend on the solution to give you an appropriate S parameter characteristic for each element as it will be presented to your power amplifier under every beam steering condition that you could apply to that array. A very powerful technique that enables you to look at large arrays with much less memory than you would have thought possible with finite element simulation. Something like this can be done with maybe 150 gigabytes of RAM on one computer. So it doesn't require an enormous HPC system to look at some fairly significant arrays. One of the things that we can develop with this, we've recently developed the capability to export a collection of files to represent or provide a reduced order model of a phased array. This is something useful for 5G modeling and simulation, where you have a collection of antennas. Each has two ports, one for each polarization. But what we develop then is a far field model of the antenna that is comprised of a collection of embedded elements. These are like individual radiation patterns for each element when all the other elements are held terminated in their nominal impedance characteristics. And it generates a far field pattern at the phase center of each one of these elements. So for this 32 port antenna, I'll have 32 individual far field patterns, each of which will be a little bit different because it's unique to the position of the antenna on its array, because you've got mutual coupling effects baked in, as well as proximity and edge effect characteristics baked into those patterns. But these become the basis of a reduced order model to then use in a later downstream shooting and bouncing ray simulation that would use this 32 port antenna as a 32 port source, right? So that I could then start to look at channel characteristics appropriate for MIMO systems and MIMO signal processing. So we'll come back to this later on when I talk about wireless channel modeling toward the end of the presentation, but a very interesting reduced order model kind of for representing phased array antennas. Now, I mentioned at the beginning of our talk here that modeling missions is an appropriate and sometimes a really necessary step in order to demonstrate how our systems operate. And here you're seeing direct output from our mission simulation software called System Toolkit. System Toolkit has the ability to model orbits of things that fly and things that orbit, things that drive, and things that float. It's a multi-domain simulation package that models realistic kinetic motion of satellites, aircraft, boats, cars, trucks, and enables you to put a variety of systems packages onto those platforms so that you can then assess, for example, radar or EOIR sensors or comm links for actual mission engagements and capture all of the links and capture thousands of analytics while a particular mission might be flying. So just think of this as a way to sort of virtually test antennas and systems, collection systems, and communication systems. So all of these platforms have RF systems on them or whatever you choose to put on them in the context of a mission simulation. So if you can simulate, for example, an antenna in flight, then we should be able to complete the stack, right? Where we start with an antenna with phased array capabilities that we want to test in the context of emission. So here's an example where we walk through that. This is I think like a 7 gigahertz antenna element here that's set in a hexagonal lattice to build up about 160 element phased array that's going to be used either for radar or for communications. This is all an HFSS model. Then we can take and place that inside of a radome and put it under an airframe, and then capture a reduced order model then of the full phased array with all of the aircraft interaction impacts so that we can then see what its phased beam phasing would look like as we apply different state vectors to accomplish beam steering with the influence of the coupling to the airframe for back lobe and side lobe, the reflections, internal reflections of the radome, right? All the things that happen in bringing the realism of where you actually put this array and mount it. Now, if you can have a good model for your array that can be beam steered, that includes the effects of coupling to the platform, the host platform, then you can set it into the context of a digital mission simulation. Here, our array is used in a communications link that is talking to a ground station. And as we simulate the flight of our host platform, we're updating our beam steering vectors periodically to keep it focused on that ground station. And you can see some really interesting things happening to the pattern, particularly at the edges of this racetrack pattern that our host platform is flying. And that's because as the aircraft goes through those corners, it's banking. It's giving the aircraft a bit of a roll. It brings the near side wing down closer to the base station, and that gets into the field of view of the main beam just a little bit. So you can see a spoiling of the main beam as we get down close and the dipping of when the aircraft dips its wings. You also see other internal reflection effects of the radome and other coupling effects that are manifest as this thing flies. And then, of course, in the system simulation, you can continually monitor things like the carrier to noise ratio or the bandwidth, the carrier to noise, ebb naught, bit error rate, and so forth for the link. Now, in our mission simulation software, we do more than just model stuff flying and driving. We also have a variety of physics that are appropriate for satellite engineering, aircraft engineering, modeling communications, both for like atmospheric scattering with vocap models and tropospheric effects for satellite to ground communications or sat to air communications. And this is across the entire spectrum. It's EOIR, it's RF domain, it's microwave domain. So if these are things that are of interest to you, you want to test long throw links, we can combine the physics of antenna modeling with the physics of long throw propagation to give you a very good assessment for what some of the links are going to be like at different times of the day, including weather and so forth. And in fact, nearly all the major aerospace and defense firms are using our tool to model that, including NASA, who's used it for modeling and prototyping very long distance missions. Let me hit real quick here the topic of electromagnetic pulse emissions. This is typically lower frequency effects, but involves very large spaces. Now, this is more of a transient effect, so we're simulating a collection of frequencies that would correspond to the typical rise and fall of a parametric EMP or electromagnetic pulse. And we have a model that's consistent with Mills standard 464, if you're familiar with that. But we can model this as a propagating plane wave that propagates either as a plane wave source or radially from some source point. But you can model the EMP coupling to other components, to antennas and cables and to the buildings and other infrastructure so that you can evaluate survivability of electronics in that context. Now, one such example would be looking at high energy effects with a propagating wave that would hit a satellite. And so here we've got a coaxial cable that would lead down into some equipment inside of the structure, but we want to know how much energy or how much current would be induced on this cable with an antenna system that we have mounted on the front of this particular satellite body. And so here you're looking at a couple of planes that capture the incoming plane waves antenna, and you're seeing the local field buildup because of the local reflections. And we have some additional contours in here showing you current density rendering as well. But you could see pretty clearly the hot spot as that parabolic antenna gathers up a lot of energy And that coaxial cable carries a pretty strong bit of current. I think you can kind of see it here, but we can also measure it with probes, which I'll show you on the next slide. You can see the voltage that's been induced on the antenna from this wave here over time. So it's a transient capture. And also see the current that's been induced onto our coaxial cable here over time. So very useful and helpful diagnostics when we're trying to understand the hardening of some of our components to events like that. Okay, let me talk a little about radar signature modeling. Now, this is capturing radar cross sections or doing radar imaging with wideband radar waveforms or doing range Doppler modeling like we see with everyday automotive radar applications. So we do this for both far field applications where usually your target is much smaller than an individual range bin. So you just want to know analytically what is the radar cross section of the target at any direction of interest, at any frequency of interest. If you have a reasonable CAD model for that target, we can provide you with an analytic model for RCS for copole and cross pole scattering. And I'll show you an example in a few minutes. But for motion-driven scenes, we can also perform near-field radar simulations, which might be also of interest from a variety of industrial applications as well as aerospace and defense applications. So for the large space analysis, typically we use shooting and bouncing rays based on the physical optics framework. Again, this is pretty well known as being a kind of a preferred method for very large target simulation. And in our simulator, we can include advanced diffraction physics like the physical theory of diffraction, uniform theory of diffraction, creeping waves, geometric object blockage, and so forth. And this is a great tool to turn to for efficient simulation of electrically large targets. It is massively parallelized so that we can take advantage of multi-core CPUs and also GPUs, and then you can take advantage of HPC, high performance computing clusters that have multiple CPUs and GPUs to compute these very, very quickly. You can see here in one case with a plane wave excitation here, all of the rays that we're taking into account as we compute these signatures. And let me just mention here, when we do ray tracing, we don't trace rays from source all the way through to an observation destination. We trace a huge number of rays to find the interaction of a local body or scatterer, and we use those rays to plant what's called physical optic currents, localized current patches that match Maxwell's equations for the reflection of a wave at that localized area. So it really begins with a mesh of the body. And then when we look at what's observed in the far field domain or at a receive antenna, we'll re-radiate all of those current patches to the observation location using a Green's function wave behavior. So there's a real wave behavior involved in this. And that again, makes sure that we're accounting for all features of our target body as well as multi-bounce interaction that might take place. Okay, when we're looking at monostatic or bistatic radar cross section, we're typically looking at single frequency impacts or single frequency effects. So you can see my single frequency RCS here for this particular airframe. But when we want to look at imaging things like range profiles or waterfall plots, which is like the range profile from a variety of observation angles, or begin to look at inverse synthetic aperture radar to capture localized hotspots of scattering, there, we're usually looking at multi-frequency simulation in addition to multiple angles. And we've got automation built in our tools to be able to provide this kind of visualization for you. So obviously, if you're doing system simulation of a radar system, you want to have a pretty good model of your target. Most systems designers start with a swirling class 1 through 4 target model, which is really just it's like a statistical variation of the radar cross section. But if you can get an analytic model, that can add a lot better fidelity to your systems modeling. And here you can see an example here of a three-dimensional RCS model for this aircraft for all 4 polarization combinations, 2 copole components and 2 cross-pole components. This data can be pushed into an archive and read up into our mission simulation software where you would actually simulate engagements against this particular target, again, with an analytical model of the full structure. And if you want to understand radar signatures for your target as it has parts that move or rotate, We have parametric control for any of the CAD models that you'd build, so that you could then repeat analyses automatically and do these repeated simulations so that you understand how the parts in motion will impact the radar signature of your target. Now, in automotive cases or in collision avoidance or industrial applications, we have radars with multi-MIMO antenna systems that we want to drive chirp waveforms against, and we want to process range Doppler information, range Doppler maps. We can do this as well. You can set up a virtual radar system model, which basically governs your waveform for pulse Doppler and chirp sequence, frequency modulated continuous wave radars, and drive that against an HFSS antenna model that you have constructed, or you could use a parametric beam antenna if you're just approximating things. Set that into the context of some location, like we have an antenna mounted on a quadcopter that's flying through this city structure, and over time we can develop animated Doppler range or range Doppler plots with an integrated forward transform, reverse transforms, or slow time, fast time transform capability against the radar data cube for every channel of your radar. Or we can supply you with the raw data for each channel of your radar in indexed by frame, channel, chirp, and sample, so that you can do post-processing on your own deck if you have MATLAB or Python or some other way of processing IQ data from your radar. We can accommodate that in this desktop, starting with the antennas and adding to the environment that you simulate. Here's just one example where we've done that. I've got a helicopter antenna. I've got a pair of antennas on the underside of our helicopter. They're 30 gigahertz antennas. We're looking down at a dry sand terrain model, and we've got a pair of tanks that are moving on that terrain, and we're simulating the illumination of this entire region by the antennas as things are moving in this environment. So it's about 121 million square wavelengths of area that we can simulate very straightforwardly, very efficiently, using our shooting and bouncing ray solver. So at 30 gigahertz, you can see here, this is a range Doppler map that's synchronized to the scene. Doppler is vertical and range data is horizontal on this map. And you can see as our various targets are moving, you can see that the Doppler bend as that one tank passes under the helicopter, and his Doppler goes from positive for approach to negative for something going away. And you can do things like this with parallel processing to knock this out very nearly in real time. It simulates very, very well. And this is simulating a waveform with 240 chirps per frame. Every chirp contains 300 frequency samples. So there's a lot of data being generated for each frame. You can also apply this to some really creative radar signature models. Here's an example. We have a blender animation of a human hand. We've put it in front of a 60 gigahertz radar with fairly wide bandwidth, and then the parametric model is up in front of our virtual antenna design, and then you can process the data as however you wish and do like image reconstruction for things like gesture recognition, and we've worked with vendors who have done that sort of work. There's another part of the toolkit that I thought might be interesting to this audience, and that is taking the antenna designs, putting them into our packages or onto our vehicles, and doing RF cosite modeling. And this gets us to understanding cosite interference and deconflicting interference problems that are from onboard RF systems, or looking at and solving link budget characteristics. Now, within the HFSS electronics desktop, we have a pretty full-featured circuit analysis tool for very detailed circuit design, functional architecture, right? And you can use that and couple it and plug it in directly to any electromagnetic model of any component that you've created. We also have an additional workflow that's more about multiple radios, not the detailed architecture of the radios, but rather provides a parametric model for any emitter or any receiver that is a wideband descriptor of the emissions. That's based on the waveform, the power level, and of course for the receiver, any characteristics that you might know about mixers and things that would be in the receiver, but they're all parametric to enable you to very quickly model wideband interference potential, in-band and out-of-band interference that would include harmonics and transmitter intermodulation products and so forth for multiple systems, tens of RF systems that are in the same platform or in the same local environment. And so what's interesting about RF CoSite is that it can doom a large platform integration project if you have serious interference issues that will require mitigation in the form of blanking receivers or moving antennas. These are really expensive things to do if you don't discover these problems until you roll the prototype into a test hangar. So we've developed this RF CoSite modeling capability to be multi-fidelity. It will start with little detail on the antennas or very little detail on the radios, but it's a model that's a living document that you can continually upgrade and improve the fidelity of the models, like the antenna to antenna coupling, once you simulate them with electromagnetic simulation, or once you even measure the emissions, the wideband emissions of a radio, you can bring that in as an input to this process to replace the previous parametric model for the radio. So having an upgradable model enables you to start the CoSite analysis process simultaneously with the design of the platform, and then can be used to even help you reverse engineer problems that you might discover in the test chamber or the test hangar later. Now, this particular modeling assessment starts, as I mentioned, with a parametric model of the any transmitter to any receiver in the problem. We develop what's called an EMI margin calculation, which is just basically looking at the received power minus the receiver's capability or the receiver's designed to reject power at a particular frequency across a very wide band. Now, receivers are designed to capture power, right, in their in-band, in-channel, but they're also designed to reject energy outside the band. So anywhere this margin becomes positive, we want to be concerned about what's going on when we're treating transmitters as signal sources that are not desirable. So here you might have a power characteristic of a particular transmitter. So we have its uh, intended signal along with a collection of harmonics that occur. Anytime we modulate signal content, we always have harmonics. We have a description of the components in the chain after the transmitter and also on the front end of the receiver that shape the spectrum, reject energy, enhance energy, could be power, an LNA in there that enhances the energy in a particular band. These models are also carried in this analysis flow. Then we have a model for our receiver. This is the susceptibility curve, basically the receiver's ability to reject energy. This is its intended frequency. So you see the IF notch here, but then there are also some other mixer birdies that create some susceptibilities for the receiver at other frequencies as well that may coincide with some of the harmonics of the transmitter to create an out-of-band interference problem. And then what we do is take that ratio all the way through to the end so that you can overlay across the entire band to understand what kind of a problem do I have? Is it in-channel problem, an out-of-channel problem? Where are the transmitters involved in this tuned when the problem occurs? Because it's looking at all the channel combinations to help me understand where I will have problems with any channel set. And then, of course, in the middle, we use our electromagnetic simulation for the antenna to antenna coupling so that we can include that to get the losses that would be from just the air gap of the systems. All right, we have about 5 minutes left. I also wanted to very quickly and briefly introduce you to a new technology that's just come out this year, literally in the last quarter, from Ansys. And this is a capability that I'll call real-time wireless channel modeling and real-time radar modeling. Now, this is built on a special shooting and bouncing rays engine. It's a special version of our engine that we've developed in conjunction with NVIDIA. NVIDIA, of course, develop very powerful graphics processing units, or GPUs, that are a little like supercomputers in a very small box. They enable a very high degree of parallel processing. And so we've been a development partner with NVIDIA for about the past 7 years or so. And have worked on mapping our shooting and bouncing ray solver to a completely GPU based simulation process. So it doesn't use CPU, it runs only on GPU. But what it takes is physics accurate models of your antennas. So the antenna models for arrays or for installed antennas that come out of your HFSS simulations. You can place them into scenes that will have motion or put them on vehicles like a car that will have motion. and then we'll produce for you IQ data for all of your radar channels, and IQ data characterizing the wireless channel link from the input of every antenna that might be transmitting to the output of every antenna that might be receiving. And we've validated this thing for scenes that have tens of thousands of antennas in a single scene. Now, again, I mentioned that it produces wireless channel models that would be appropriate for someone to use in a complete link layer simulation in a communication system model. But we also have embedded it in our own AV Accelerate toolkit for automotive radar and autonomous driving simulation. Here you're looking at 6 range Doppler maps that are being computed simultaneously for a 77 gigahertz radar as it's driving through a city scene. I don't know if you can see this very well, but there are other vehicles. Some are approaching, some are driving in the same scene. We have approaching street lights, we have curbs, we have all these structures in the environment that are creating reflections that are then showing up in our range Doppler maps, where range is vertical, Doppler is horizontal. And you can see the activity going here. And it is simulating actually faster than real time for these 6 radars being simulated simultaneously on a single moving vehicle. And on this side, of course, you see the we're computing channel modeling to do massive multi-user massive MIMO beamforming that's based on the pilot signals used in a 5G system. Here we're computing the pilot signals back to the base stations every 10 milliseconds of real world time. And this simulation actually runs about 3 times faster than real world. So that processing is actually computed in about 3 milliseconds of actual wall clock time to characterize 10 milliseconds of channel activity in the world. Now, this is an API-driven simulation engine. So this is something that people can connect to using C++ or Python programming scripts. It operates on NVIDIA, high-end NVIDIA Quadro and Tesla GPUs, and will automatically load balance on nodes that might be equipped with multiple GPUs if you're looking at very large problems. So we've already sort of developed the ability to parallelize across multi-GPUs, but you'll find very good performance on a GPU that would contain about 12 gigabytes to 16 gigabytes of onboard RAM. Now this is right. It's something that requires you to do a bit of your own programming, since it is an API accessible only kind of formulation. Not everybody wants to do all of their programming to break the environment down into mesh triangles. So we've taken this solver engine and put it together with our mission simulation software so that we can give our customers the framework to combine their high fidelity antenna models that come from HFSS, bring them together with high resolution virtual environment models like the cityscape or a mountain terrain or city terrain, and the buildings and all the structures and constructs that go into an environment, along with a plan for the subscriber and access point motion for how things fly, drive, orbit. Bring them together in a product called the Ansys RF Channel Modeler to automate all of this in a very visual, graphically rich environment to generate all of the channel model data that we want to then use later to attach to like a physical link layer simulation deck. So here's an example of this brought together. This is our system toolkit mission simulation software that has models of 3 5G base stations, each with 32 ports. You can see the model for that antenna. We have the installed antennas. We've got a shark fin antenna here on a couple of Range Rovers that are driving through the environment. And then we're modeling the connectivity from our host or from our vehicle to each element of each array. So this is 192 channels that we're simulating. The model of Denver here, and this is actually based on LiDAR measurements of Denver overlaid with photogrammetry, has 5 centimeter resolution across 10 square kilometers. And we're modeling all of the multipath, the diffraction, the absorption, all of the things going on in this environment. In this case, at 10 millisecond intervals for all of the channels across a 100 megahertz bandwidth centered at 3.5 gig or 3.8 gigahertz. And you get I think you get the picture. It's a very high amount of data in a very high resolution environment. And these models for the environments are available through the cesium system, using the cesium ion format to spool and exchange these cityscape models. So if I just look at one channel of, this is the connectivity now from a flying platform, a quadcopter or some kind of a UAS platform, to one element of this phased array. I'm just going to picture it here just for one channel. So it's, I think, horizontal to horizontal coupling. You're looking here at what amounts to, across our 100 megahertz of bandwidth, these are forward S parameters. This is S21 real imaginary that characterizes the signal or the voltage that travels from the input port of the transmit antenna to the output port of one of those phased array antennas. And it's vector information, so it's complex frequency response. Now, if you take that complex frequency response with a large number of samples across the band, you can get the delay spread characteristic, right, which becomes the basis of a multi-tap delay line model to represent the physical channel from our subscriber to the access point. And that's changing. Here we're showing you every tenth of a second, I think, to try to keep the density of display down a bit. But you can see how there's the incident wave would hit with a certain delay, which is the first major spike that you see. But you see many secondary delayed spikes that are because of the multipath in the environment and the diffraction transmission through the environment. Now, again, this data is computed at real time with this solver, which is the real value of this. And then if we can roll up, of course, our channel characteristics over the entire scenario engagement over 120 seconds here, and you can see frequency representation and time representation. And again, all of this is coming out in this, or has come out in this package called Ansys RF Channel Modeler. All right, I apologize. I think I'm a couple of minutes over, but here are my takeaways. High performance physics modeling for high and low frequency systems, a wide variety of challenges and problems. Use these to validate RF systems in the context of a design reference mission simulation by coupling those physics models into our system toolkit for mission simulation. You can create direct, accurate analytical models for your RF signature disciplines. And again, with RF Channel Modeler and the Perceive EM solver, we can now provide high quality RF and radar signature modeling at scale and at real-time speed. It's possible now. So thank you. I appreciate your attention and the opportunity to talk to you about these things. I can hang out here for another few minutes if there are questions, or we'd be happy to follow up with questions after the webinar time here. But Laura, I will pass it back to you to close things up.
Yeah, thanks a lot, Shawn. I think it was very interesting. I must say thanks for even covering the real-time RF channel simulating tool for us as well. There's a lot of good things covered during this session. Really appreciate your effort, and thanks for everybody attending. I'm going to stop the recording now, and then we can have time for questions. Okay?